Welcome to this introduction to addressing modes, a fundamental concept in a computer architecture that defines how a computer accesses data or operands during program execution. An addressing mode is a method that specifies how the location of an operand or data is provided with an instruction. Understanding addressing modes is crucial because they offer programming versatility, giving you the flexibility to access data in various ways. Additionally, they help optimize instructions, reducing the number of bits needed in the addressing field, which leads to more efficient code. Why addressing modes are used? Addressing modes allow programmers to work with the data in different ways. For example, accessing data from registers, memory, or even immediate values. This flexibility helps in writing efficient and varied programs. Reducing the number of bits in an instruction by using different addressing modes, instruction can use fewer bits to represent where the data is located, optimizing the memory usage and making instruction shorter. In immediate addressing mode, the operand is provided directly within the instruction. This means that data needs to be operated and is explicitly stated without requiring any memory reference. For example, in the instruction add 5, the number 5 is the operand. This tells the processor to add the value 5 directly to the accumulator. The key advantage here is speed, as no extra memory access is required to fetch the data. Everything the processor needs is right in the instruction. However, one limitation is that the range of values that can be provided is restricted by the size of the instruction. The data has to be within the instruction's bit width. Look at some examples. Move AL, 25H. In this instruction, the hexadecimal value is 25H is immediately moved into the register AL. There is no need to fetch data from memory. AL is set to 25H instantly. Another one example, move AX, 2345H. Here, 2345H is located into the AX register. After execution, AX will hold 234H, where AH becomes 23H and AL becomes 45H. In direct addressing mode, the instructions address field contains the actual memory address where the operand is stored. This means the effective address or EA is simply the address provided in the instruction. For example, in the instruction add A, the processor looks at memory location A to find the operand. The contents of memory address A are then added to the accumulator. This mode requires a single memory reference to fetch the data, making it straightforward to use. There are no additional calculations required to determine the effective address, as it is already given in the instructions. However, the trade-off is that direct addressing has a limited address space depending on how many bits are allocated to address field in the instruction. In indirect addressing mode, the memory address provided in the instruction does not hold the operand itself. Instead, it points another memory location that contains the actual operand. So the address field acts as like a pointer. The effective address is determined by the first looking at the contents of the address specified in the instruction and then using that value to find the operand. For example, add A. The processor first looks in the memory location A But instead of finding the operand directly, A contains another memory address. The processor then goes to the second address to fetch the operand and add it to the accumulator. The process requires two memory references, one to fetch the pointer, the memory address stored in A, another is to retrieve the actual operand from the memory location specified with the pointer. While indirect addressing provides flexibility by allowing access to a wider range of memory, it comes at the cost of extra memory access, making it slower than direct addressing. In register addressing mode, the operand is stored in the one of the CPU's internal registers. Instead of pointing to a memory location, the address field of the instruction directly refers to a CPU register that holds the operand. Since the operand is already inside the processor, there is no need for memory access, which makes this addressing mode extremely fast. However, it comes with some limitations. The number of available registers is usually limited, meaning that the address space is smaller compared to the other addressing mode. But this also allows for a very small address field in the instruction, resulting in shorter instruction that can be fetched more quickly. In this example, the instruction add or increments the value stored in the accumulator by the contents of the register, or we can express this operation mathematically as in the following manner. This addressing mode is closely related to direct addressing mode. The key difference lies in how the operand is accessed. While direct addressing refers to a location in the main memory, here the address field of the instruction points directly to a CPU register. By utilizing registers for operands, we achieve faster execution because accessing data from register is significantly quicker than fetching it from memory. This results in efficient calculations and improved performance for the processor. In register indirect addressing mode, the address field of the instruction points to a CPU register that holds the effective address of the operand. This means that the actual data is not directly referenced. Instead, the instruction uses a register to indicate where to find the operand. With this approach, we require only one reference to memory to fetch the operand. For example, consider an instruction add or. This operation will increment the value of stored in the accumulator by the content of the memory location specified in register R. This can expressed mathematically as in the following manner. Here, the outer brackets indicates that we first look at register R to find the memory address, and then we fetch the operand from that address to add it to the accumulator. In indexed addressing mode, the effective address of the operand is calculated by adding the contents of an index register to the address specified in the instruction. This method provides a way to access an array or data structure more efficiently. The formula for determine the effective address is given here. The approach allows the program to reference a range of data in memory without needing to adjust each instruction manually. For instance, if the index register contains a value that points to the base address of an array, adding the instructions address part allows the program to access specific elements within that array. This mode is particularly useful for operations and data structures such as arrays where the base address is known and the index can be varied dynamically during execution. In relative addressing mode, the effective address of the operand is computed by the adding the content of the program counter to the address part of the instruction. This method is often considered a version of displacement addressing, allowing for dynamic addressing based on the current location in the program. The effective address calculated by the formula effective address is equal to content of the program counter plus address part of the instruction. This addressing mode is particularly useful for control flow instructions such as jumps or branches. It enables the program to access operands relative to the current instruction location, which can facilitate easier code manipulation and relocation. For instance, when executing a branch instruction, the processor can quickly calculate the target address by using the current value of the program counter, which points to next instruction, and adding the specified offset from the instruction itself. This ensures that the program can jump to the correct location seamlessly. Auto increment addressing mode is a special case of register indirect addressing mode. In this mode, the effective address of the operand is simply the content of a designated register. The key feature of this addressing mode is that after accessing the operand, the content of the register is automatically incremented by a defined step size denoted as D. This step size typically depends on the size of the operand being accessed, such as whether it is a byte, word, or double word. The effective address can be expressed as effective address of the operand is equal to content of a content of register. With this approach, only one reference to memory is needed to fetch the operand. This is particularly useful for processing data structures like arrays, where successive elements can be accessed in a loop. Auto decrement addressing mode is a specialized form of register indirect addressing mode. In this mode, the effective address of the operand is determined by subtracting a defined step size denoted by D from the content of a specific register. The effective address can be expressed as effective address of operand is equal to content of register minus step size. In this mode, the process begins with decrementing the content of the register by the step size d, which typically correspond to the size of the operand being accessed. After this decrementing operation, the operand is read from the newly calculated effective address. This method allows for efficient access to data structures like arrays in a reverse order as it enables access to previous elements quickly. Thank you for watching.